So in the previous discussion, we talked about the mobile phase, the column matrices, right? How to fill the column, how to equilibrate the column. Now, when it's how to load the column, all these things in details we talked. Now it is about the solvent system. So when it is to a chromatographic solvent system, uh, when we talk about column chromatography, so elution is the term. Elution is the mobile phase which you are allowing to run down the column. The mobile phase passes down the column, and then the fraction that reaches to the other end of the column is collected at the control rate that we have seen in the previous lecture, that diagram also. So what kind of mobile phase are you going to use? Is it going to be a uniform single solvent, or is it going to be multiple solvents together in proportions, or a single solvent with changing concentrations? That is how you can use. So the term which is used for elution, the types of solvent systems, one is isocratic. In isocratic system, only one solvent is passed to the stationary phase. And in the second type, that is gradient system, different solvents with predefined ratios are passed through the stationary phase to separate the components. Now, isocratic, when I say iso is same, right, to single, but here the component is one factor. Secondly, temperature could be another factor, right? Elution temperature also matters. Of course, it is not to be talked right now here, but in this case, you have to remember a single solvent system is used in isocratic, and gradient system uses multiple solvents. Their proportions are prefixed, pre-decided, or pre-researched and then used, or maybe a single solvent with its changing concentrations also can be used. Now, just take an example of the gradient elution technique, right? So, when we talk about elution, the components of the sample that is applied, it is going to get separated by continuous passage of the mobile phase down the column. That is very important, right? And the flow rate for the same is very adjusted. So this is talked about as elution development of the column. During the elution process, it is essential that the flow of the mobile phase, it is pre-decided and is to be maintained. It should be at a stable rate. Generally, as I said earlier, it is achieved by gravity. So gravity is not going to change, and effect of gravity on individual particle is going to be dependent on characteristics of the particle. So the flow rate also is not going to change. But of course, this flow rate can be regulated or changed by adjusting the operating pressure. So a difference between the level of the liquid in the reservoir and that in the column, and the level at the outlet of the column. All these are to be taken into consideration, and you can set the flow rate. So generally, a simple open reservoir for the of the column is not sufficient. If you want to set the rate, you have to have a the reservoir which can be operated with the help of a pressure pump, right? So the design is going to be again like reservoir. To that, a pump is attached. So specific amount of pressure is applied that is going to allow specific volume of the mobile phase at specific time, speed, right? So many microliters per unit volume. That is how it can be. So is allowed to come out of that reservoir, and then it will be entering the column. Similarly, the exit or the outlet or the eluent also will be collected at a fixed rate, right? Uh, the stable flow rate using the peristaltic pump is quite easy to maintain, and there won't be any errors. Most commonly, the pumps are of roller type, right? So these are going to deliver the mobile liquid phase through silicon or polyvinyl chloride tubing, and by compressing the tubing, the reservoir disc is rotated at a rate that is predetermined and the flow rate is achieved. So the volume is sucked at a particular rate and it is allowed to enter the column. Now, when it is single solvent, it's fine. But when it is gradient elution, you have more than one solvent and you have to mix those two mobile phases or two liquids in particular proportion, right? As against if it is isocratic elution, you are going to use a single liquid as mobile phase. But can you change the resolution power or the efficiency of this single mobile phase, the single solvent mobile phase or isocratic mobile phase? Yes, you can continuously change the pH, you can change the ionic concentration, or you can change the polarity. Again, you are varying something in that solvent system. So again, it becomes gradient type. It is single solvent, but you are changing the pH. So gradient of pH is set. You are changing the concentration of ions. So ionic mm, parameters you have to adjust. So again, it is going to be the gradient with respect to ionic concentration. Or similarly, another factor that is polarity. You may go from low polar to high polarity or vice versa. So again, there is a gradient with respect to polarity of the solvent system. So though it is single solvent, it will be called as gradient solvent system. Now, to produce a suitable gradient system, you may mix two solutions, two solvents also, as you are seeing in the slide. There are two reservoirs having two different solvents, solvent A and solvent B. They are to be pre-mixed at a pre-designed proportion. So this is the pump which is attached, and by capillary that are you are seeing here, the vessels are connected through the pumps, right? And the tubing channels. So this at a particular rate from this solvent system, solvent, and at a particular rate from this solvent, so solvent A and solvent B, particular volumes will be mixed, and that will be regulated by this pressure pump, which is going to allow that mixed solvent system to enter the column at a particular rate. And it is moved down the column, and then at the other end of the column, the elution pump are attached, which are going to collect the volumes at a particular speed. Again, the rate, flow rate, outflow rate also is specific, and then you are going to analyze it with the help of analyzers. The analyzers in details, the detectors and analyzers in details will talk. What are the different methods? Are they connected to any other instrument like spectroscopy, spectrophotometer, etc., etc.? That we will talk about the detector later. But just to give you an idea about how the gradient would be prepared, it is solvent A and solvent B. They are mixed together with the help of the pump, and they will be entering at a particular rate into the column. So commercially available gradient mixtures are available. Similarly, the mixing systems, commercially available mixing systems also are there. So the two elements are you are seeing are placed in separate chambers, and the recipient chamber is attached to it, and it is attached to the column through the donor chamber. So you have two different chambers for two different solvents. You have a pump, you have the donor chamber, and you have the column. So that is how you can uh, see the design of a gradient elution system for a column chromatography uh, design. Again, here you can decide the pH. Again, in here you can decide the pH, the ionic strength, or the polarity of the eluent. And these variations can be adjusted to achieve better separation or good efficiency or good resolution of the analytes. So with this, we talked about the elution technique, right? So in that you have process two different techniques. One is isocratic elution, another is gradient elution. Isocratic is single reservoir attached to the column at a particular flow rate, it runs down. But when it is gradient, you have to have the idea that which two different solvents you are going to select, at what pH, what ionic concentration, at what rate they are going to get mixed, at what time of column running. So a single solvent is used. It is a single element system. But when you are going to have more than two solvents with differing pH or molarity or ionic concentration, polarity, then it becomes a gradient system. Now here, one is important thing is the flow rate, which is denoted by capital F, right? So it is talked in terms of volume of mobile phase per unit time. The flow rate of the column mobile phase is very important criteria when we talk about the column development. So if you want to get really good resolution, it is very necessary that the eluent flow is maintained at the stable rate. Not only the reservoir that is going to pump the mobile phase onto it, it is attached to a fixed flow rate, but the elution also is carried out at a fixed flow rate. Now, how to maintain this stable flow rate? So again, here you use the peristaltic pump to force the eluent onto the column. In a similar way, a peristaltic pump can be attached to remove the eluent out of the column. So increase in the flow rate of the mobile phase to the column. If it is more, if it is very fast, then in short time you will get the separation, but there is no guarantee that it will be adequate. At the same time, very long separation time with very slow flow rate, very less flow rate also may not serve the purpose. So it is very important to optimize the maximum possible flow rate that would give us a good performance in the liquid chromatography. But if if you increase the flow rate of the mobile phase, then due to that flow rate, a pressure is continuously there. So column matrices may get compressed and separation may not be good. So in this case, the distribution of analytes between the two phases will not be taking place adequately and separation will not be good. So here comes the role of high pressure liquid chromatography, HPLC, that we will discuss separately in the next lecture. But flow rate of the column chromatography is an essential component and that needs to be optimized. The flow rate should be in between to maxima or minima. You cannot see like that, but you have to adjust the one which will be efficiently giving you best possible resolution and in minimum time. So as I said earlier, if time is reduced, fast elution will occur, but separation will not be good, and vice versa. So you have to optimize the flow rate, which will give you good resolution, efficient resolution, and time required also is less possible. So the flow rates used are going to be uh, different for each type of analyte. It cannot be the same for all analytes because every analyte is going to interact with the stationary phase differently. So you cannot have one single particular flow rate, even though the column size, column height, all these things are same. Depending upon the nature of the analyte and depending upon the nature of the stationary phase and that of the mobile phase, the optimum flow rate is to be determined. Of course, just to uh, uh, generalize the method, commonly used flow rates, they are generally between 30 to 120 ml per hour per cubic centimeter area. So here the factors are volume of the solvent that is going to enter or elute from the column, the time that is in hours, and area of the column. So 30 to 120 ml per hour square centimeter. These are the generally used flow rates for column chromatograph. Of course, the flow rate is going to get affected by column packing. Unevenly packed columns will lead to distortion of the flow and the flow rate will get affected, and ultimately it will affect the resolution. Good separation cannot be obtained. So densely packed column, if you talk about, so that there is no airspace, no gap, that is good. Uniform and densely packed column. But uniform and densely packed column is good for uniform flow. But if it is tightly packed, the rate of flow of the mobile phase will be affected. It will resist the flow of mobile phase through it, and the flow rate will get automatically reduced. So it is very important to pack the column optimally so that it functions well at a good flow rate, right? So these are the few things to be remembered when we talk about mobile phase and its working. So it's not just only to choose a solvent system and a mobile phase that is adequate and good for the chosen analyte, but it is very important that at what rate it flows down the column. That flow rate of the mobile phase or elution is very, very critical and important, that will decide the success of your separation system or chromatographic separation. Now here in the next slide, we'll take an example to continue with the gradient elution. Just to connect back, gradient elution is one where you have more than one solvent and maybe varying in pH, ionic strength, polarity, etc. So during gradient elution process, here an example of protein purification is taken. The salt concentration is the parameter which is changed, and few millimoles to higher millimoles, say 10 to 50, for example. It can be varied when we talk about the concentration of salt. So here, let's look into the example. The salt concentration is decreased gradually. Gradually as in linear fashion. एकदम random changes नहीं है. 10, 9, 8, 7. There is a continuous linear decrease in the concentration from high salt concentration to low and a defined volume. Right? So, like we talk about the rate, here also you have to talk about the uh, the nature of the gradient in terms of concentration, that is amount of salt per unit volume. So during initial screening of a bound compound on an adsorbent, the salt concentration may be decreased to as low as 0 millimoles to determine salt concentration when the product elutes. So starting is as low as 0, right? So a typical gradient elution process, if you talk about, is performed over 10 different column volumes, and during which the fractions are collected. So from 0 to 10, you will have 10 different concentrations, and that will each concentration of the eluent, the eluent with each concentration of the salt will give you one fraction of the sample. So 0 to 10, so 1 micromole or 1 millimole, depends on the system, to 10 millimoles. So 10 fractions. So for each of these, you will get 1 aliquot of the analyte, and you will get to know how it is affecting the separation after analyzing that eluent. So the gradient in the salt concentration may be decreased, and you can use larger volumes. So resolution, as I said earlier, the volume, the time, and the resolution, these three factors are to be optimized. So if you are imagining a column where you are trying to separate protein and the gradient elution is done, and the gradient elution mobile phase includes salt gradient, right? So what can happen? The possibilities are that the protein remains bound to the adsorbent in the column. It doesn't come out easily, right? So this will indicate that the protein is attached more strongly to the matrix, right? Matlab it is weakly interacting with the mobile phase that you have chosen at a particular salt concentration. So it is weak interaction with the salt. So lyotropic salt should be selected to bind the protein to the adsorbent. Or the in simple words to say, the salt that you are going to choose should have a strong attractive force for the protein, so that the protein analyte gets dislodged from the matrix and has strong interaction with the mobile phase. So you can choose a weaker lyotropic salt, so that you can select, so that protein's adsorption onto adsorbent can be reduced. Maybe you can go with stronger elution conditions, so faster elution of the protein from the column can be achieved. But stronger elution conditions क्या होंगे? Maybe you are going to use a solvent system where organic solvents like polyethylene glycol or acetonitrile or ethanol are incorporated. So the interactive forces of these organic solvents towards the protein without affecting its um, um, native structure and functionality should elute it out from the column. इससे उल्टा और क्या कर सकते हैं? You can reduce the interaction between the protein and that of the matrix. So adsorption जो हो रहा है matrix में, that can be reduced. So you have to choose a matrix which is going to have weaker interaction with the analyte. So an adsorbent with weaker hydrophobic binding strength may be selected. So it will decrease the strength of hydrophobic interactions. ये hydrophobic interactions are occurring between what and what? The adsorbent material and the protein. Protein is not going to, or any analyte is not going to get retained in the matrix due to strong chemical interactions. But there are weak interactions, ionic interactions, salt bridges, van der Waals forces, hydrophobic interaction, that is analyte का hydrophobic and the column का भी hydrophobic force. So hydrophobic interactions, they are going to occur, and they can be very well overcome by using a appropriate mobile phase, which is going to be more interactive with the analyte rather than the adsorbent. At the same time, second approach could be reduce these hydrophobic interactions of the adsorbent, so it will not hold the analyte for longer time. All right. Now, probably you get to know now what is happening. Yesterday's and previous TLC के जो lectures थे, that in that we have talked about what are the kinds of interaction between the support matrix, stationary phase and analyte, and mobile phase and analyte. So partitioning between the two and adsorption onto stationary phase are going to be the factors which are going to decide the elution. So if your mobile phase is selected in such a way that its interaction with the analyte is stronger, the analyte will come down the column, elute from the column easily. Now here is just to get you an idea, how do we get to know whether that process is adequate or not? So your column chromatography system is running, the solvent system is passing down, the analytes are getting separated, and your elution channel also is operated at particular speed. So at a certain period of time, you are getting some volume of the elution. You are going to collect these fractions. So column से नीचे जो run out हो रहा है at a particular time interval, particular volume, that you are going to collect and analyze it for the sample analyte that you are interested in. So it will give you an idea whether it is appearing in fraction 1, appearing in fraction 2, at what time interval, so on and so forth. लेकिन this is to automize or converted into graphical presentation. So your system is attached to say spectroscopic method. So as the analyte is there in the fraction, your system is attached to spectroscopy. Spectroscopic analysis will be done and it will be telling you this is the absorption at this particular nanometer at this particular time interval. Right. So the data will come up as table and also can be come up in the form of graph. The graph is, as you are seeing in the slide here, on the x-axis you have elution volume. So at first 5 ml में आया, या first 10 ml volume में से analyte आया, या 100 ml में आया, that fraction, right? So elution volume is on x-axis, और उसका जो signal आएगा using the detection system, that is plotted onto y-axis. So it is absorption that is given at a particular wavelength. For example, 200 nanometers, 300 nanometers, 280 nanometers, for example, in this case, that absorbance is checked and that will appear as a peak. So it tells us that spectroscopic system is attached to your column chromatography, and whatever the analyte is coming as a part of the fraction separated and as appearing in the volume. So first 50 to 100 ml में कुछ नहीं आया है, right? But after 100 ml volume, you start seeing appearance of the analyte and the peak grows and it drops. So you are getting a very good separation because the peak is very precise, right? And then after at 150, again there is a drop and there is another peak appearing, which is for some another analyte, which is absorbing at around, say, just match with the y-axis. It is about 130, 140 nanometers. The first peak is matching at about 280 nanometers. So an analyte which absorbs at 280 nanometers is there in the first peak. At the second peak, it is the analyte which is absorbing highest at around 130 or 135 nanometers. So these are two different analytes which are having different absorption maximas, right? So this is how you will get the chromatogram. Now in this case, elution is done with 10 millimolar salt NaCl at pH 6 and then 50 millimolar sodium phosphate. This is the final elution system. Then the gradient is prepared wherein gradient from 50 millimolar NaCl to 150 millimolar NaCl in the same buffer at flow rate 2 ml per minute is used. So as a result, the mixture has got separated into two different fractions and the two different zones, and the fractions collected are identified and they will tell you what analyte is present in this and is present in this. Of course, when you are adding some salts in the sample analyte, maybe the absorption properties of your analyte also will get changed and its lambda max also may change, right? So it may give you separate peaks with change in gradient, and at what particular mixture combination the analyte is appearing earliest, right? Earliest on x-axis you see first few ml मतलब fast आ गया बाहर, earliest and with highest efficiency, that would be the right combination of your mobile phase. But it is not eluting the entire fraction, so you have to go on preparing the gradient elution buffer and apply it, and so that you get two different fractions, and these fractions can be analyzed for the analytes present in the given sample, right? Now this is last but one slide. There is one more slide and we will conclude for today. So it is comparison of isocratic against gradient. So एक ही sample है, एक ही system है, लेकिन you are seeing isocratic gradient system, right? And isocratic system and gradient system. So this is in previous graph what we had seen. What was there on the x-axis? It was with respect to volume. Now it is with respect to time, right? X-axis, and y-axis is with respect to conductance. So some other instrument is attached here for analysis. Conductivity is measured, right? So you can have any detector system attached and scanning system attached to the chromatographic column for analysis of fractions and analysis of the analytes that are coming out in the eluent. So here the graph is with respect to time and conductance. Again, so पहले पे क्या था, यहाँ पे वॉल्यूम था, तो वॉल्यूम विल कम एट पर्टिकुलर टाइम. 5 मिनट में 10, जो पहला वॉल्यूम निकला 10 था, लेकिन 10 मिनट में निकलेगा डबल वॉल्यूम आया होगा. So time or volume you can plot on x-axis and the response on the y-axis. So if you are seeing कि what kind of graph and how to read it. So if you see the isocratic separation mode, ये पहला जो longest peak है, it is always that of the solvent that is used, basic solvent, and these small peaks are that of the analyte which are in the solvent system, which are present in the solvent system and are appearing after a particular period of time, right? So you have A to F analytes. F is last appearing and first appearing is what? A. So A is appearing first. So is it interacting more with the mobile phase or with the stationary phase? Because it is eluting out, that means it is interacting more with the mobile phase, and F is retained most, coming out last. So it is having more interaction with the support matrix, stationary phase. Right? In this case, the scenario is totally changed. All of them have come out in a specific time period. Here you will see A, B, C are fast eluting compared to E, and F is the last one to elute. At the end you are seeing lot of time is required. Here it is not the case. A to F all have come out in the half the time of the reaction. That means this gradient elution is giving us better efficiency. Again you see the peaks. Here are precise fine peaks. Here they are merged. So separation is not adequate. The B and C is together, A is with the solvent. That means the complete purification of the analyte is not done. They are still mixed. So the B and C are giving you a merged peak. Here in this case, B and C are totally separate. So the gradient that is used is giving you good separation in half the time. So that is one important thing. Now, the solid lines which are showing these peaks, right? They are the fractional distance migrated by each compound between column inlet and outlet. आप वॉल्यूम के बारे में बात करो, आप टाइम के रेस्पेक्ट में बात करो, या फिर द डिस्टेंस माइग्रेटेड के बाद कंपैरिजन में भी you can narrate the data. And the dashed lines, they indicate instantaneous K prime. What is K prime? In the TLC we have talked about, it is partitioning coefficient. कि how the analyte is getting partition between the two phases. Stationary पे कितना, mobile पे कितना. So that K value is going to be dependent on the fractional distance. जैसे आपकी RF value होती है TLC में, वैसे ही that RF value is going to tell you about how strongly the analyte is interacting with the stationary phase and how analyte is interacting more with the mobile phase. If it is more with the mobile phase, it will come out fast. All right. So partitioning coefficient will shift towards the mobile phase is taking the analyte out fast. That means 0 to 1 are the values for K prime, partition coefficient. This is what we have seen in previous lectures. So it will be 0 if equal distribution is there between the two. क्योंकि ये ratio है. So amount of analyte in the stationary phase upon amount of analyte in the mobile phase. That ratio if you take, it will give you K prime. Concentration of analyte in one phase upon concentration of analyte in another phase. This ratio tells you about partitioning coefficient. So if distribution is equal in both, that means there is K prime value is 0. But if it is changing like 1 upon 1 upon 0.5 or 1 upon 1.5 like that, so K prime value will change. And if it is indicating that more activity with mobile phase, that means good elution time, fast elution. So time can be adjusted according to that. So these two graphs are telling you about the difference of separation, adequate resolution of a column chromatography analysis system if you use isocratic system as seen in diagram A, and if you use gradient system as you see in diagram B. So with this, today's discussion is done from my side. If you have any queries, please do write in chat.